what we're going to look at next is something called molecular geometry. So molecular geometry is related to the 3D orientation of the atoms in a molecule. So the way this is different than electron geometry is now what we're worried about is where are the atoms at. So we'll start by saying this. If there are no lone pairs on the central atom, then the molecular geometry, Mg, is equal to the electron geometry. They're the same. So in cases where there are no lone pairs in the central atom, then there end up going to be the same answer. That's because everywhere there's an electron to separate from another electron group, there's an atom at the end of it. So the atoms are then in the same place as the electrons. What changes is lone pairs. So when you have lone pairs, these take up space on the molecule. So on the central atom, because they're electrons, and that's where a lot of our shape actually comes from, is the electrons. But when they're taking up space as electrons, there's no atom on the other side. Another important point is that they take up more space because they are only on the central atom. So what happens when we try to draw these molecules is the lone pairs, because they're going to take up extra space, are going to push everything else away. And this is going to change the bond angles we're working with. So that's why this matters so much. So when we have lone pairs, we're going to have new shape names. So once you've learned the electron geometries, those match up with the molecular geometries when there's no lone pairs. But you're going to add some additional molecular geometries for each case where there are lone pairs in the central atom. We now have a new shape. So let's look at some of those. So we're just going to go through each of the possible shapes. So you don't have to worry about the linear shape, because if you take away an atom, you still end up with just two atoms and they're aligned. And if you get down to one atom, I don't have a name for the molecular geometry of one atom by itself, because now it's not a molecule anymore, it's an atom. So we're always going to have at least two atoms. And whenever you have exactly two, you have a line, because that's the only way to think about the orientation between exactly two objects. So we're only looking at cases, well, if you ask a case where there's two atoms only, it's linear. So anything beyond two is what we're concerned about. So we're going to start with the example we did in the last video that I said we were going to get to, SO2. So SO2, and I'm not going to worry about I'll draw those since they're relevant for knowing it, why this is right. So what's important here is we identify not just the electron groups. We can do that first. Electron groups, there are three, but we need to differentiate. There are two bonding groups and one lone pair. So if you go and look at one of those tables that I talked about in the last videos, the giant table that has all the shapes, this is how it's going to sort them when you get to molecular geometry, is how many electron groups first, and then it's specifically going to look at lone pairs. You could also do bonding groups and lone pairs together, since by looking at the group for that, effectively if it's 2 and 1, it's got to be 3 for its electron geometry. But my general recommendation is find your electron geometry first, then find out how many lone pairs you have. And there'll be a shape name for that. So 3 electron groups with 1 lone pair has a shape name. Its name is bent. So where does bent come from? Well, for the molecular geometry, what you start with is you draw it like it was just the electron geometry at first. So we have a sulfur, and the electron geometry says that for 3 groups, you get a trigonal planar setup. So we'll put one of our oxygens here, one of our oxygens here, and then the lone pair goes up here, and it takes up some space. So for the electron geometry, this is still okay. It's still trigonal planar because the electrons are in 3 spots surrounding the sulfur. But the molecular geometry, that's not right anymore, because this doesn't have an atom at the other side. It's only these two. So if you took your triangle and ripped the top off, the 2 left over make a bent angle here. That's why we call it bent. I will also note that this shape can be a slightly annoying name because there are two different shapes that end up with bent, but they end up with different bond angles. And we'll mention it when you get there, and some books will rename one of them angular to help deal with this, but we're going to call them both bent because that's what most people seem to do and what most texts do. So this one is bent, and specifically it is less than 120 degrees. So you may ask me, wait, why did you say less than 120? Why not an exact number? Well, the reason for this is 120 is the correct angle for a trigonal planar molecule. This lone pair, because it's on the central atom only, takes up more space. It acts like a bully and pushes both of these oxygens in. So we know it shrinks the angle. So it's close to the original angle. The original angle was 120. And it shrinks it down so that it's now less than. The issue is the exact amount it shrinks is going to depend on the structure of the molecule and what other atoms are around. So we can just say less than 120. It could be 119, it could be 118, it could be 118.5, something like that. It's going to be smaller, it's not going to be 109.5, but it's going to shrink some. So we just write it as less than 120, unless you've done a measurement of some type and use some technique to actually find the exact angle. There's no reason to memorize those as a giant pile. It's only if you really need it for a specific reaction where you would actually find out what that was. And you can search for it. We've experimentally measured that. But what we're going to say for what you're going to look at is just it's less than 120. Now, let's do some more shapes. So that's the only time we have to worry about electron groups 3, because if there's two lone pairs, we just have two atoms, and we'd say it was linear. And the linear means 180. So let's do some more electron groups. So let's look at things where they have 4 electron groups, because here we have 2 different ones to worry about. So all of these start as tetrahedral, but we start putting lone pairs in places where there aren't going to be atoms. So we're going to start with NH3. NH3 has 1 lone pair and 3 bonding groups. There we go, 3. I realized you can't read sideways 3 like that. So we have a nitrogen. We have 1 hydrogen in the plane of the board, 1 going away from us, 1 going into the board, and the one on top. But the one on top is going to be our lone pair. Note, I'm only drawing the lone pair on top because it is the easiest way to draw it and think about it. The lone pair you could orient so it's there, there, or there. That's fine. I just think this shape is easiest. So we started with a tetrahedral. Remember, the tetrahedral was you had a tripod, so you got 3 things, all linking up to 1 thing in the middle, and then you had another atom on top. Well, you ripped the atom off top that made it a tetrahedral. So now you just have your triangle. Well, you'll notice if it's 3 things going down as a tripod, these 3 hydrogens also form a triangle. So you end up with a trigonal pyramid. So this name is trigonal pyramidal. That is its molecular geometry name. The electron geometry is still tetrahedral, but the molecular geometry is trigonal pyramidal. It has angles of less than 109.5 degrees because tetrahedral is 109.5. This lone pair pushes them together. Now, let's look at one other case. So this was the 1 lone pair case. Let's look at the 2 lone pair case. Let's look at water. So for water, we end up with 2 lone pairs and 2 bonding groups. So you have an oxygen, you have 1 hydrogen, and you end up, if you look at how you end up orienting these, you're able to get both hydrogens to be in the same plane. It's like at this one and this one. And then you end up with 2 lone pairs that are taking up some space. So now what happens is since you just have 3 atoms, but they're not in a line, if they were a line they'd be linear, but they're pushed together. If they're pushed together, this is our other bent molecule. But in this case, the angle is now less than 109.5 degrees rather than less than 120, because it started at 4 electron groups and then lost 2, didn't lose 2. 2 of them were lone pairs. So those 2 lone pairs don't have atoms on the end, and they're able to push everything together. So now we have this shape, less than 109.5. The final note I want to make here is, in addition to these both being less than, generally, this shape that only has 1 lone pair, while it's less than 109.5, it's also going to be bigger than the one that has 2 lone pairs. So if we were to think of this, let's take CH4, for example, has no lone pairs. We were looking at it in the last video. And so it is exactly 109.5 degrees. So if you wanted to list the bond angles in order, CH4 would be the biggest, which would be bigger than our angles for NH3, which would be bigger than our angles for H2O. So to think about how they arrange with each other. So these are our shapes for 4 electron groups. If you had a third lone pair, you would be down to only one other atom and you would be linear. So let's take a look at 5 electron groups now. So since you've already done the electron geometries, you may know we're getting close to the end because I need 5 and then I need 6. And there's one other thing I'm going to talk about for a minute on this video. So for 5 electron groups, we have a new complication to worry about. Now we have to worry about, we mentioned there were equatorial and axial atoms. So they're different because one was 120, one was 120, one was 90. So they're not the same, so it depends on which ones you take. Well, I'll let you know that what you do is you always take, in the case of 5 electron groups, you remove the equatorial atoms, the axial atoms stay. It's not as stable a structure to try to take the axial atoms, so it's always the equatorial atoms that go. So we're going to start with SF4. This is the case where you have one lone pair. So, just to show you how I got that, if I did the Lewis structure, so I'm not worried about shape yet, I have sulfur bonded to 4 fluorines. So we'll review this. Now, we know that electron-wise, each fluorine, there are 4 of them and they bring 7. That means 28. Sulfur, there's 1 of them, it brings 6, that's 6. We add that up and we get 34 electrons. We've used up 8 so far drawing the bonds, so we have 26 electrons left. So we go 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. Means we have 2 left over, 1 lone pair goes on the sulfur. So now this shape, while it is fine for a Lewis structure, is not what the molecule would actually look like. So let's draw what it actually looks like now. So we have our SF4. So remember, we want to think of it like a trigonal, our trigonal bipyramidal from before. So we had a triangle in the middle and then 2 fluorines on top. So we know we said it never comes off the axial, so the fluorines stay on top. Now I'm going to draw my fluorine here and my fluorine here, and then I'm going to put my lone pair out here. Note, it would be fine if any of these was the lone pair, but I'd like to draw it in the plane of the board when possible. It makes it easier to talk about the molecule. So this is the shape it takes on, which means this angle now here is going to be less than 120. So between that part, and then you're going to end up with less than 90 here between this fluorine and those, because the lone pair is basically pushing everything together. So the lone pair is on one side, and then everything else is on the other, and the lone pair is pushing harder, and it makes everything like squeeze in on itself. So we end up with less than 120 and less than 90. This shape is known as the seesaw. The reason it has this name is if you literally rotate it, these 2 fluorines make the 2 fluorines here act like the bottoms of a seesaw, and these 2 fluorines are where the 2 people are on, the top and the bottom, and so it can go back and forth. It's not the best name in the world for it, but once you remember it, it can sometimes be easier to see it, maybe. I don't love the name, I'll admit, but I didn't get to pick the name, and whoever did, other people seem to like it. So it's seesaw. That's our shape. So that's 1 lone pair. So now, I took up too much of the board. I'll have to do another shape for 2 lone pairs. So for 2 lone pairs, we're going to work with the molecule BF3. Wait, does BF3, I mean BF3, I mean BRF3. See, this is why you have to learn all your rules, because then it's not that you don't make mistakes. It means you can look at them and go, wait a minute, that's really wrong. And then you can fix them. I definitely make mistakes, though. I just learned how to fix them faster. And you will too. Just take some time, and that's okay. So BRF3, when we get its structure, so if we just draw it as a Lewis structure, well, I'm going to draw it. This is what its shape would be. We just did a Lewis practice a minute ago. And I don't want this video to take you forever. You end up with 2 lone pairs in the equatorial, and then you have 1 on bottom, 1 on the side, 1 on the top. Thankfully, this one has an easier name in this case. It's T-shaped. See, so we have a T-shaped molecule. So this one's usually easier to name because of that. Now, if you took away another atom, and you can for XEF2 if you do it, so I guess I'll just do that one. So this was 2 lone pairs. Now, what I'm going to look at next is the molecule XEF2. Now, if you were in my course right this moment, unless you're watching it in a future year, maybe we decided to change it, we don't deal with trying to make molecules out of these noble gases. Technically, there are a few that do exist, though. So I'm going to show you the shape this would take, And if you were to have to do the Vesper shape for exactly this, I would give you the Lewis structure because it's weird. Wait, xenon has 8. Why does it need more? So, XEF2 does this. And has 3 lone pairs down here. Well, linear. So this is our 3 lone pair case. And because we've removed all the equatorial atoms, we're now a line. Means we're also 180 degrees. Because these two are as far away as possible from each other. So, I mentioned that the noble gases, there are a handful that make a small number of molecules, and at least at the time of this recording, basically, honestly, everyone I can think of. Maybe there's another, but everyone I can think of is some different number of fluorines attached to a noble gas, and that's because fluorine is so electronegative that we can get it to bond to a noble gas. Even the noble gases basically never want to bond to anything. If you do enough work, you can get fluorines onto them, not much else. So, also to point out, if you were doing the Lewis structures to finish the problems, don't forget to put the lone pairs on the fluorines. So, that's our 5 electron group case. Now we'll finish off with our 6 electron groups. So for 6 electron groups, the rule is going to be the opposite of what it was for the trigonal bipyramidal. These always put lone pairs in the axial position instead. Lone pairs axial. So for this, we've got 2 examples to look at. We have Br F5, and so this is going to have 1 lone pair. So the way we end up doing that is we put a bromine, and then we have our fluorines. Those are easy. And then it doesn't matter if you put it on top or bottom. You can put the lone pair wherever. I'm going to put the lone pair on bottom. It's fine if you put it on top. So remember, this was an octahedral shape before, with all 90-degree angles. Well, now we have less than 90-degree angles, because this lone pair is going to push everything together. And we're going to get a shape that is a square pyramid. Because before an octahedral was a square pyramid on top and on bottom. These 4 make a square. Thing at the top, everything goes to the same top. That's what a pyramid does. And then the bottom was another pyramid. So you chop the bottom atom off. Well, now it's just another pyramid. It just only goes to the top. So we call this square pyramidal. The final shape we'll talk about, this is the last electron geometry we'll do, will be for 2 lone pairs. And we're going to do XE of 4 for this. And again, this is something I would give you the Lewis structure for if you were in my class currently, at least. Because we haven't been doing things with xenon where we had you actually do it because it should already bonded, we figured. So we have a xenon. We connect it to 4 fluorines here. I'll fix that. And then we put a lone pair on top and a lone pair on bottom. And we get square planar. So you literally have a square. And now we're back to 90 degrees because the 2 lone pairs, because they're on top and bottom, yes, they both want more room, but they're exactly opposite each other. They both push the middle together in the same amount, so we end up with these are exactly 90-degree angles instead, because they're able to counteract each other. So with that, that is the last of our molecular geometry shapes, and I mentioned I want to do another topic. I'm going to do that in the next video, because this is a good place to stop this one.